My name is Tomas Hernandez, and I will present a summary on the paper Control Barrier Functions for Non-Holonomic Systems under Risk Signal Temporal Logic Specifications by Lindemann et al. The author's contribution include defining risk signal temporal logic, which is an extension of signal temporal logic to model risk in stochastic systems. Therefore, risk signal temporal logic specifications can be used for control systems in stochastic environments. The authors then proved that risk STL can be translated to an STL specification, which transform a stochastic control problem into a deterministic control problem, and therefore we can use any existing control method for systems under STLs. Finally, time-varying control barrier functions, which include the previous work from the authors, are applied to solve for the first-time control in continuous time systems in unknown environments under STL specifications. We define x of t as the signal and is the time-dependent state. Capital X is the environment variable. In signal temporal logic, we will have predicates of the form mu STL that depend on a predicate function h. We say that the predicate mu STL is satisfying at time t if and only if x of t is such that the predicate function is greater than or equal to 0 when x is deterministic. The goal is to consider the case when x is a random variable. We define two new types of predicates. The chance predicate is true only if the probability of satisfying the STL predicate is above a threshold delta. The risk predicate is true only if the risk of not satisfying the STL predicate is below a threshold gamma. Risk signal temporal logic is defined by incorporating the chance and risk predicates into the syntax of STL. The semantics are defined recursively. A triplet x, capital X, and t satisfies the chance predicate if it is true under those parameters. The triplet satisfies the risk predicate if the risk is less than or equal to gamma. The rest of the semantics are similar to STL. Furthermore, a quantitative value is defined for each formula component. The important property to note is that a triplet satisfies the formula phi if its quantitative semantic rho is positive. Now we define the problem statement. Given a dynamical system, environment variable with known mean, variance, and distribution, and giving a risk STL specification, we should design a control function U such that rho is positive and bounded by R with R maximized, which means that the risk will be minimized. We define the sets where the chance and risk predicates hold true, and we define with a design parameter a set xm of Cm using the mean of the random variable x. Note that this new set is deterministic. Our objective is to show that the set x of Cm is a subset of the satisfaction sets, so that an x from this set also satisfies the chance and risk predicates. An important result is that if we assume that the predicate functions are linear in x, we can show this set of exclusion can be efficiently computed via a convex program. With an appropriate design parameter, a risk STL formula can be translated to an STL formula by replacing every chance and risk predicates with their deterministic counterparts. We arrive at the main result of the paper. The authors proved that for each of the n predicate functions that form the STL specification, an appropriate design parameter can be found such that the STL specification being satisfied ensures the risk STL specification is also satisfied. Now, relying on previous work, giving an STL specification, it is possible to design a control barrier function that encodes it and a controller that satisfies it and is forward invariant. The authors provide an example where capital X encodes 4 regions with the specification to sequentially reach R1 and R2 while avoiding regions O1 and O2. This specification is encoding in risk signal temporal logic with 7 predicates. Simulations using time-varying control barrier functions yields the paths indicated in the triangles. Note that the trajectory does not try to reach R1 from above O2 as it is deemed too risky. The trajectory attempts to stay away from O2 to reduce risk. In conclusion, the authors define risk signal temporal logic, prove that risk signal temporal logic specifications can be translated into STL specifications, and then use time-varying control barrier functions to solve for the first time control on continuous time systems under specifications in stochastic environments.